Welcome back to Bio 6612. So today I'm going to cover effect modification, also known as interaction, and interaction and logistic regression. So most of this and what I cover in the next lecture on confounding is review from 6611. So I'm not going to cover it in too much detail. So when doing an analysis of the relationship between two variables, an outcome, which we call y, and an exposure, which we'll call x, it's important that the investigator take into account other variables, which sometimes we'll call z, that may alter the association between x and y. The interaction or effect measure modification, which is when the relationship between y and your primary exposure of interest x varies by some other covariate c or z. Confounding is the distortion of an estimated association due to the effect of other variables. And generally speaking, if a variable is an effect modifier, then we consider that effect modification first, and its role as a potential confounder is secondary. So we're going to look at an example of interaction with this teeth discoloration data. So we're interested in whether the antibiotic called tetracycline causes teeth discoloration. And we have data that is grouped by age, where we have data for children and for adults. And so effect modification or interaction occurs when an effect is thought to vary across strata. In other words, the relationship of interest is different at different levels of the extraneous variable. And in this case, our extraneous variable is age, children versus adults. And so the odds ratio for the combined data from that previous slide is 1.52. And that's the odds ratio comparing the relationship. And that's the odds ratio for the relationship between the antibiotic and teeth discoloration. However, the odds ratio for children is 1.7 and for adults is 0.92. So the odds ratio actually goes in different directions for children and adults, in that it's positive for children and negative for adults. So this looks like evidence that there might be effect measure modification. So if we have evidence that the odds ratio or some other measure of association that we might be interested in varies by level of some extra covariate, age in this case, then it doesn't make sense to present a single measure of association between the exposure and the disease. We want to actually instead present a measure at each level of the extra covariate. And this is called the stratum-specific odds ratios or conditional odds ratios. When we say conditional, I mean conditional on the covariate. So you would have an odds ratio given age is child, and then you'd have a second odds ratio given age is adult. Those are your conditional odds ratios. So, but in order to see whether or not that interaction is actually significant, we can test that using an interaction term in a linear model. So in the R code that's printed below, first I actually define a data frame called discoloration by inputting the data that we saw in that table. And then I'm going to build a logistic regression model with teeth discoloration as the outcome and tetracycline as the covariate of interest. And this is just a 0 if you did not receive tetracycline and a 1 if you did. Here you can grab the coefficients of that model and exponentiate to get the odds ratios, and here you see I am not using an interaction term for this model. This is just the odds ratio for the combined data. So if we do actually want to test for the association, then we're going to be interested in the model printed below in this model here. And that allows us to test if the association between teeth discoloration and tetracycline varies by age. And in this model, you have your intercept, You have X1, which in this case is tetracycline, whether or not it was received. You have X2, which is age, young versus old. And then you have your interaction term, which is X1 multiplied by X2. And so the hypothesis test that we're actually conducting here is, for the null hypothesis, the association between teeth discoloration and tetracycline is the same for adults and children. Or equivalently, you can test that beta for that interaction term is equal to 0. And the alternative hypothesis is that the association is not the same for adults and children, which is equivalent to testing that beta 3 is not equal to 0. And this is, as I said before, this is your interaction term, and these terms that are not multiplied together are known as your main effects. So what are our results of running that model? Well, we can run the model in R by putting in each of those covariates of interest and then multiplying them together to get the interaction term. And the summary of those coefficients is presented below. Your betas are here. This is going to be beta 0, beta 1, beta 2, and beta 3. And then the p-values are here. So in this case, the p-value for the interaction term is p equals 0.285. So that's less than 0.05. So if you have alpha is 5%, you're not going to reject your null hypothesis here. So there's no evidence at the 5% level of significance of interaction. And typically speaking, if an interaction is found to not be significant, we remove it from the model. So let's look at another example, and back to that passive smoking data set. And so here we're interested in the association between passive smoking or secondhand smoking and lung cancer. But we have an extra information in the form of another covariate called smoker, and that's whether or not a person smokes. So the outcome of interest is cancer. The covariate of interest is this passive smoking, whether you're exposed to somebody else smoking, and then this sort of third covariate that might modify the association is smoker, and that's whether or not the individual in question personally smokes. So we have data that I've loaded into R here, and the pooled data for the odds ratio for the association between cancer and passive smoking in the combined data is 1.64. In the subset of smokers, that odds ratio is 1.3. And in the subset of data of non-smokers, that odds ratio is 2.09. So as you can see, the odds ratio in the non-smoking group is quite a bit higher than it is in the smoking group. And in this case, the effect isn't reversed across strata, it's just different. And that's okay. Like, it can still be considered an interaction if it's not reversed, as long as it's different. So is this interaction significant? Well, the first thing I'm going to do here is I'm going to change the reference level of the covariate smoker. So I'm taking the data set, which we called passive, and then I'm using the mutate function from the dplyr package to say, okay, the variable smoker, we want it to be a factor variable with the levels no and yes. And so the reason I'm doing this is I'm just explicitly telling R that I want no to be the reference level and yes to be the second level. So now I build that model. Again, cancer status is the outcome. And then we also have, and then I just did passive smoke times smoker. So the last time I built an interaction model, I wrote out what would be passive plus smoker plus them multiplied together. I could write that out in this R code here. However, it's equivalent to just write out the interaction term. R automatically includes the main effects for you. So it's just less code to write it this way than it is to write it this way. So is that interaction significant? We're going to assume that here we actually decided to have an alpha level of 0.1, just so that I can show you of what the interpretation looks like and what you do if you have a significant interaction term. So yeah, we're interested in that. Here we have beta 0, beta 1, beta 2. We're interested in beta 3. And the p-value for that beta is 0.071. So we would reject, if we are test at the 10% level of significance, we would reject the hypothesis that beta 3 equals 0 and conclude that there's sufficient evidence to conclude that the association between passive smoke and lung cancer depends on, or you could also say varies by, personal smoking status. And because you do not reject the null, sorry, let me restate that. Because you do reject the null, you would report the stratum-specific odds ratios, and that should just say alpha. And so that interaction term, beta 3, can be interpreted as the additional increase or decrease. In this case, it's a decrease because the estimate is negative in the log odds for smokers exposed to passive smoke beyond the additive effects of personal smoking and exposure to passive smoke. And to interpret the association between passive smoke and cancer, we need to examine the parameter estimates for both passive smoke, that is beta 1, and the parameter for the interaction term, beta 3. We can't just interpret beta 1 anymore because beta 3 is in the model and depends on passive. So let's use this equation to calculate the relative odds of cancer for individuals exposed to passive smoke compared to those not exposed to passive smoke. Because this interaction term is significant, that odds ratio of the association between passive smoke and cancer also depends on personal smoking status. So for smokers, the log odds ratio is going to be here. So basically you have, you include the intercept, and then you multiply by 1 for passive smoke, and then you multiply by 1 for smoker because this is the smoker group, and then you subtract by the beta for the interaction term. And it's multiplying by 1 because these are both indicator variables. X1 and X2 are both indicator variables. If that was a continuous covariate, then instead you would plug in the value of that covariate for the person whose odd ratio you're trying to calculate. And then you just exponentiate that value to get the odds ratio. And for non-smokers, it's similar. We start with the intercept, this 7.739 term. Stays in the model. This next term, the smoker, here smoker is equal to 0 because this is the non-smoking group, so that term drops out, and this last term also drops out because smoker is equal to 0. So in the last slide, we looked at the odds ratio of cancer comparing those exposed to passive smoke versus those not exposed. But what if we want a different odds ratio? For a different effect. So for example, what's the odds ratio of cancer for smokers compared to non-smokers? Again, it depends on passive smoke because the smoker covariate is in the interaction term. But for those not exposed to passive smoke, now we're going to be looking at a ratio of odds ratios. So for the passive smoke category, we have passive smoke equals 0 throughout. But on the top here, we're going to have everything where X2, that's the smoker variable, is equal to 1. And the bottom, we have X2 is equal to 0. So you start with that beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, no, x1 times x2. And you go through and you multiply all of that out. And so for the first term, you have the intercept beta 0. For the next one, in this case, x1 is 0 because it's the passive smoking group, so that term's going to drop out. Then we have x2 equals 1 here on the numerator, but x2 equals 0 in the denominator because that's the group we're trying to compare. And we're also going to have 0 multiplied by the interaction term. In this case, it would be 0 times 1 times beta 3 on the top, because we have a 0 for passive smoke, a 1 for smoker. And on the bottom, it would be 0 times beta 3, because on the bottom, we have a 0 for passive and a 0 for smoker. And then because of the properties of dividing exponential terms, so if you have e to the a over e to the b, for example, that's going to be e to the a minus e to the b. Sorry, e to the a minus b. So because of that property, you're going to have any terms that are in both the numerator and the denominator cancel. So you're going to have the beta zeros cancel. And that's the only one there that's in both. So what you're left with for the first odds ratio for those not exposed is the same thing. It's just exponentiating the beta 2 term, the beta for smoker. But it gets a little bit more complicated for when you're looking at those who have been exposed to passive smoke. So in this case, on the numerator, we're looking at people who have a value of x1 equals 1 and x2 equals 1. And in the denominator, we have x1 equals 1 and x2 equals 1. So plugging that into the same set of equations, you end up with, for that odds ratio, you're going to have e to the beta for smoker plus the beta for the interaction term. So what if I wanted to get a confidence interval for those quantities? That I calculated in the previous slide. So for those not exposed to passive smoke, where passive equals 0, the term was a little bit simpler for the odds ratio. It's just e to the beta for smoker, so that's just e to the beta 2. And the confidence interval you can calculate using the Wald the Wald statistic, which we used in the previous slide, and the standard error, which is already output by R. However, for those not exposed, it's a little bit more complicated. So what we want is, now we have this whole term of beta smoker plus beta of smoker and passive, and we want the confidence interval for that. And to get that, we're going to need, so that's the same thing as beta 2 plus beta 3. And so for that, we're going to need the variance of beta 2 plus beta 3. Which is written down here. But you can simplify that to the variance of beta 2 plus the variance of beta 3 plus the covariance of beta 1 plus, sorry, I messed that up for a second, plus 2 times the covariance of beta 2 and beta 3. And where this, from this step here to this step here, where that's coming from, that's a property of variance and covariance, where you have, if you want the variance of the sum of two random variables, A and B, that's going to be equal to the variance of A plus the variance of B plus 2 times the covariance of A and B. And in your first homework assignment, you were able to distribute something that was like variance of y1 plus y2 and say that's equal to variance of y1 plus the variance of y2 with no covariance term. This second rule here, that's only going to be true when y1 and y2 are independent. So in our case, we cannot assume that the coefficients beta 2 and beta 3 are independent. So we have to include this covariance term. So then you get this big complicated term for the standard error of beta smoker and beta smoker times passive, which is given here. And there is a way to use R to recover those values and then calculate that confidence interval. And so it's written here, the equation again. And so you can use R, you can use say you have a model that's defined and it's called mod, then the R code is cov V of that mod will return what's printed here. And this is the variance covariance matrix for the betas in your model. And so the first thing that we need is the variance of beta smoker, or I'm going to call it beta 2. And that is found on the diagonal of smoker. So that is right here. Similarly, the variance of beta 3, you find where passive smoker is, and then you also find where the variable passive smoker meets the row for it meets the column for it. That's right here. That's going to be your variance of beta 2. Sorry, variance of beta 3. This one was variance of beta 2. And then the covariance between beta 1 and beta 2, beta 2 and beta 3, is okay, you want the covariance between passive smoke and the interaction term. So in the row, I look for passive smoke, and then I see where it meets the column for the interaction term, and that's this one here. Or I could do the same thing I could do is I could look for the interaction term and see where it meets the coefficient for beta 2. And that should be the same value, and it is. So you can plug those all in to this equation here and get your value for your standard error. But clearly this is kind of complicated and a bit of a pain to do by hand. So an alternative to that is using what are called contrast statements. And both R and SAS have ways to get estimates and confidence interval for contrasted parameter values of interest using these so-called contrast statements. So the way that works is, take the coefficients from your model. In this case, this is beta 0, beta 1, beta 2, and beta 3. And you set up a contrast matrix. So In this case, we're going to set up a contrast matrix that will allow us to get confidence intervals and estimates for the odds ratio of passive smoking for non-smokers, the odds ratio of passive smoking for smokers, odds ratio of smokers for those who are not exposed to passive smoke, and odds ratio of smoker for those who are exposed to passive smoke. And these contrasts basically multiply times each of the terms in your model and say which ones that you would want depending on what covariate pattern you're interested in. So here, this is like saying, okay, we're for passive smoking for non-smokers is giving you, okay, a 1 for the passive smoking column and a 0 for everything else. Secondary, we have, in the second column, we want passive smoking for smokers. That's again a 1 in the passive smoking column and also a 1 in the personal smoking column. Then the odds ratio of smoker for those exposed to passive smoke. And then so for the two odds ratios associated with the odds of cancer for smokers, looking in the passive smoke versus no passive smoke category. Now we're more interested in these second terms, or interested in always having smoker, and whether or not you're exposed to passive smoke is what changes. And contrast statements can get rather confusing. So I'm gonna go through and do an example in lab of this as well and walk through it in a bit more detail. But basically what you do once you set up one of these contrast matrices is multiply it by the coefficient terms to get your odds ratios. And then you multiply, or you multiply it by your variance covariance matrix. This is just the matrix version of what we did before when we did, this is just the matrix version of a multiplication here. And that will give you your standard error for your odds ratios. And by running that code, you can see now we have, and actually going back for a second here, this isn't actually your odds ratios. I should have called that log odds ratios. And these are your standard errors for your logs odds ratios, not your actual odds ratios. And then going over here, you exponentiate those log odds ratios. And e to the to get your odds ratios for each of those different parameter combinations in this first chunk. This next chunk gives you your lower confidence interval, and then this last one gives you your upper confidence interval.